Okay, today I'd like to talk a little bit about one of the most important things that we use as scientists to accurately and precisely convey our measurements in our scientific research. So we do the scientific method, we do experimentation, and then when we report values, which are a number and its units, then we have to take into account what are called significant figures. And the significant figures reflect both accuracy and precision. Now, we in everyday common speech tend to use accuracy and precision somewhat interchangeably, but in a scientific context, well, in actually all contexts, they do have slightly different meanings. Accuracy, if you say something that is accurate, we say that that's how close it is to some sort of actual value, which means that you happen to know what that actual value is, or you have a specific thing that you're shooting for, and if you get close to that, then that's a measure of how accurate you are. If you're precise, that's how close your measurements are to each other. So if we're doing the same measurements on the same thing, so if you and I are taking the mass of something and we both get values that are close to each other, then we say that our values are precise. In terms of a visual, we like to think about it in terms of our bullseyes here, which you can see there's not very good precision amongst my bullseyes. But if we're shooting here for the center of the target, and I have a lot of values that are really close to each other, and they're all right in the center, then we would say that this is both accurate and precise, right? So it was really close to the center of the bullseye, and all of my measurements were pretty close together. So I must have been a good shooter, or a bow shooter, or a dart thrower, or whatever it was that got me at the center here. Archer. So if we go to this second one, and we say, well, I got all of my arrows or my darts or my shots close together, but they weren't at the center, and assuming I was shooting for the center, then I would say that it's not accurate. So not accurate. But my measurements are pretty precise, right? They're clustered pretty close together. And there's value in that as well, because if you have precise measurements, but they're all off in some way, then that might indicate some sort of systemic error, something that's wrong with the process that you can then fix. Now, if I have marks that are all over the board and maybe ones that are off, if I was throwing darts or if I was shooting at things, it'd probably be more off in this kind of area. So if we have a bunch of values that are kind of all over the place, then we'd say, well, it's not accurate at all, right? It didn't hit the bullseye, and my measurements aren't precise at all either, right? So not accurate, not precise. Now let's think about this in terms of a concept check. Is it possible to have the other way around? Is it possible to not be precise, but to be accurate? So think about that for a second. It's kind of hard to wrap your head around, right? How could I have a precision? How could I not be precise, but I could hit the same spot over and over and over again, right? So it can't really happen that way unless you're just doing one measurement. And then that's not very valuable either, because we know that the scientific method is built around reproducibility, sharing our results, doing experiments multiple times, etc. So let's think about what this looks like in terms of a measurement. I've drawn this very artistic pencil here. And if I wanted to take the length of this pencil, which I'm going to do with my ruler that's in centimeters, then if I give you a ruler that looks like this with no other markings on it, then you would say, well, my end here is at 0, and the tip of my pencil is about right here. So if I kind of draw a line straight down, then if you were going to guesstimate this, the length of this using this tool, then you would say, well, I'm for sure about the 3. It's definitely 3 centimeters. And then kind of what it is, the wiggle room between 3 and 4, because there are no other markings, then I have to guess that digit. So 3 point, I don't know, what do you think that is? Maybe 3.4 centimeters. Okay? So what I've implied here is that this digit that I reported is a guess. And I'm always going to report out to the guessing digit. And this reflects the precision of my measuring tool. If I was to have a measuring tool that had all of the markings in them, so let's give me some 5s here, and then I can give myself some 2, 3, 4. So if I had a tool that did have all these gradations in there, right, then I would say, well, I'm for sure about 3.123. 3.3 I'm certain about. But then in between 3.3 and 3.4, so kind of that small distance between there, I'm not sure, so I'm going to have to guess. I'm going to say it's 3.32 centimeters. And that implies here that this last digit that I've reported is my guessing digit. So you can see the greater number of digits that I have, the more precise I can show that my measuring tool was, because that last digit reflects that there's always going to be some wiggle room, and we consider that the reported value is plus or minus 1 of that last digit reported. This reflects the uncertainty of your measurement. And it's important to report that last digit, that guess digit, because I'm saying that I think this measurement right here is between 3.3 and 3.5 centimeters. I think it's somewhere in that range. As soon as I got a more precise measuring tool, then I said, well, I think this is between 3.31 and 3.33 centimeters, plus or minus the last digit reported. And that gets me into more and more precise, more and more accurate potential for my measurements. And the number of digits that I report here is going to reflect my measuring tools. And my measuring tools could, in some cases, just be my eyes, right? It could be something that I'm using that's either something that's part of me as a human or a tool that I'm using in the laboratory. Okay, so the number of figures, the number of numbers that I report in my measurements are called significant figures, and we affectionately call them sig figs as scientists. So you often will see us write sig figs on your quizzes and exams when you don't have the right precision and accuracy that is reflected in your measurements. So this is going to be important moving forward. Once you learn about sig figs, you always have to take into account significant figures. And there's two major things that significant figures give us. They give us a way, first of all, to express the certainty of our measurement, and that comes from that expression of plus or minus 1 of the last digit. Second, they're a tool by which we can round the answers that we get when we're performing mathematical operations. So we're adding, we're taking a logarithm, we're dividing, and once we have an answer that our calculator spits out, this gives us a way to round that answer so it accurately reflects the measurements that we performed. So significant figures are very, and pardon the pun, significant to scientists. And here's the rules. Here's how we determine significant figures. It's kind of all about the zeros. The first one is that all non-zero numbers are significant. So if I have a number that is something like 3.45 feet, then I have 3 significant figures here, 3 non-zero numbers. So here's my 3 sig figs. So being able to just recognize how many significant figures are in a number is an important skill, because that reflects that this measurement is somewhere between 3.44 and 3.46 feet. Zeros between non-zero numbers are significant. So I grew up in California, and my area code there was 707. So my area code also has 3 significant figures. That 0 that is sandwiched between 2 non-zero numbers is also significant. So this has 3 sig figs too. Now zeros at the end are really the trickiest. So if I have zeros at the end of a number, they're ambiguous. And what I mean by ambiguous is that we can't really be certain unless we ourselves did the measurement. So we can make them less ambiguous by the way that we report them. If I have a number that's like this, 300, and let's say it's 300 meters, because these zeros come after the non-zero, so I have my non-zero here and 2 zeros, these guys, I'm not sure if they're significant or not because they're ambiguous. And the way that this is written, we would say that this has 1 sig fig. because I can't be certain. The only one that I'm certain of is the non-zero at the beginning. So there's a couple ways that we can make this less ambiguous. We can put it into scientific notation, which is always the go-to. As scientists, we're going to use scientific notation, and that disambiguates or makes less ambiguous the value that we're reporting. So this one is 3.00, and these zeros that come after a decimal are significant. So that's the tricky part. So this is 3 sig figs. So here's the difference between the two. We have zeros after the non-zero with no decimal place. That means they're not significant. We have zeros that are after a decimal, and that means they're still significant. Now, if I wanted to express 300 as having two significant figures because of my measuring tools, then I could still express it in scientific notation, and it would be 3.0 times 10 to the second meters, which gives me two significant figures. Here's my 2 sig figs. Okay. So far, so good. Nice and clear as mud. That's the worst part right there. That rule number 3 is the worst. Now, leading zeros kind of fall in the same rule. So zeros to the left, I'm talking about a value that has something like this. So let's make this energy. So if I have 0.0042 joules of energy, which isn't very much, then these zeros really just show me where the significant numbers start. The non-zeros are significant, but if I was to write this in scientific notation, which again, we're scientists, so that's what we would do, then we would write this 1, 2, 3 backwards. So this would be 4.2 times 10 to the negative third joules. And we can see here there's two non-zeros, and that gives me two significant figures. Now, it was two significant figures either way. It was 2 sig figs here, it's 2 sig figs here. It's just clearer to see when I write it in scientific notation. So when in doubt, write it in scientific notation, because that's going to make it easier to be able to determine how many significant figures there are. Okay, so let's look at another example. Let's do something like this. And what do you want that to be? Let's say it's an area. So if I have 0.0310 centimeters squared, and I said, how many significant figures are in this number? Then you would say, well, there's some zeros in there, so that's going to make it tricky. But I know for sure it has 2, right? I know if these 2 non-zeros are. There's a decimal in here, and there's some zeros that are leading, so I'm going to write it in scientific notation in order to make this less ambiguous. So when I write this in scientific notation, I'm going to keep everything that comes after those non-zeros. This is going to be times 10 to the negative 2 centimeters squared. And now when I look at this, then I have 3.10. So the question is this zero significant? And we said that if we have zeros at the end, they're ambiguous. But if they come after a decimal place, then they are significant. So this is a significant zero. This would have 3 sig figs. And this is one of the most challenging things, is to figure out kind of our Sig Fig rule. So what if I said, well, how about I have an 8,000 pound elephant? So I have an 8,000 pound elephant, and I want to express that mass with 2 sig figs. So what is that with 2 sig figs? Well, if I said, okay, well, I'm going to round this to 2 significant figures, then I'd have to say, well, I need to write it in scientific notation, because all of these zeros make it ambiguous. So I'm going to say 8.0. That has 2 significant figures. That 0 is after the decimal place, so it's significant. And then times 10 to the third, which represents the place of where all those zeros are. And then my unit. Remember to always have units. Always take into account significant figures. And we'll talk a little bit more about how we round and when we use them in mathematical operations in another video.